Recursive math. All right, let's look at some examples of some recursive functions. These are not necessarily functions that you would write, but we're going to try to reason over how they work mathematically. So for that, we'll go here, we'll copy this, and we'll paste it here. And here's a bunch of functions. And at the end, here's a function that when you run it, it calls the functions above after asking for which function you want to run. So what we're going to do here is show you the function. This first one, what's going on here? Well, it's the function f1 of x where it's f1 of x is 1 more than f1 of x minus 1. Well, what function, when you increase x by 1, increases y by 1? And we would naturally think about y equals x, right? Or say f1 of x equals x. Because if that's true, is that 1 plus f1 of x minus 1 is just x minus 1. That's actually the case. So we go here, we'd expect this to be f1 of 0 is 0, f1 of 1 is 1. In fact, so it is. The answer is f1 of x equals x. So now that was maybe a way to get the answer, or like if you knew to think of it recursively that way. But there's another way to go about this, and that's just to build up your table bottom up. We know that f1 of 0 is simply 0 because of this line right here. Well, f1 of 1 is 1 plus f1 of 0, which is 1 plus 0, so that's just 1. And by the way, for now I'm just going to say f for this function. F of 2 is 1 plus f of 1, which is 1 plus 1, so that's 2. And so now we see we're off to the races. We can apply the same logic here, and what we'll see is, in this case, calling this function f of 0 is naturally 40 because of this line here. And then we're going to go up by 1s again. F of 1 is 1 plus 40 is 41. F of 2 is 1 plus f of 1, which is 42. So it's 40, 41, 42, and so forth. And if we come down here and see that, there it is, 40, 41, 42, and so forth. What about this one? Well, so it seems like whenever we're adding some constant to f recursively, we're getting a linear function. So we're going to guess this is linear, and it's going to grow by 2. So we're going to get 0, 2, 4, 6, 8. And indeed, the answer is 0, 2, 4, 6, 8. So that's the evens. Pretty cool. This one here sure looks like the evens again, only starting at 40. Indeed. What about this one here? All right. So in this one, we're no longer adding a constant to f, but we're in fact adding a variable. We're adding x to f, which means that as x increases, the change increases as well. So let's look at what's going on. F of 0 is 0. F of 1 is 1 plus f of 0, which is, I get 1. F of 2 is 2 plus f of 1, which is 2 plus 1, or 3. F of 3 is 3 plus f of 2, which is 3 plus 2 plus 1. And now we're seeing a pattern. Aha, it's so-called triangular numbers. Let's come down here and enter in a 5. And sure enough, you see the difference goes up by 1, then it goes up by 2, then it goes up by 3, then it goes up by 4. Those are the triangular numbers. Okay, so f of 6, this one's a little more complicated. It's actually easy to figure out by plugging in numbers what's going to happen, but how would you look at it and figure it out? So in this course, we don't expect you to look at something like this and to mathematically determine what it is. But you can plug in numbers and say f of 0 is 0, f of 1 is, well, that's going to be 2 minus 1 is 1 plus f of 0. F of 2 is 2 times 2 is 4 minus 1 is 3 plus f of 1, that's 1 plus 3. F of 3 is 6 minus 5 plus f of 2, so it's actually write this one this way, 3 plus 1. 5 plus 3 plus 1. And it looks like it's the sum of the odd numbers increasing, which is true. Actually, f of 4 is 7 plus 5 plus 3 plus 1. But there's something else really interesting that happens here. And that is the sum of the odd numbers happens to have another nice property about them. Well, 3 plus 1 is 4. 5 plus 3 plus 1 is 9. 7 plus 5 plus 2 plus 1 is 16. It's the perfect squares. Okay? And if we go down here and run f of 6, it is the perfect squares. Now, there's another reason why. Like, if you consider x minus 1 quantity squared, that equals x squared minus 2x plus 1. All right? So now let's solve for x squared. We find that x squared equals, we add the 2x and we subtract 1, and we get 2x minus 1 plus x minus 1 squared. Okay? And here's your 2x minus 1, 2x minus 1. So if this function computes x squared, then the f of x minus 1 computes x minus 1 squared. If we add this value to it, sure enough, we get x squared. So this is why this function works. That's a little complicated, and honestly, for 112, this is f6 is a pretty cute function that you can largely ignore. f7, well, so let's look back for a minute, because most of this is important. I think f6 was less important. f1 is very important. When you add 1 each time, you get a function that adds 1. You can change the starting point. That's what f2 showed us. When you add 2 each time, you get a function that adds 2, and you can change the starting point. Here we added x each time, and instead of getting a linear function, we got a quadratic function. Now instead of adding, we're multiplying. Aha, let's see what that does. It changes function families on us. f of 0 is 1. f of 1 is 2 times f of 0, which is 2. f of 2 is 2 times f of 1, so that's 4. f of 3 is 2 times f of 2, so that's 8. Aha, it's the powers of 2. So let's punch in 7 here, and 1, 2, 4, 8, 16. It's the powers of 2. So the difference between 2 plus f7 and 2 times f7 is dramatic, as it turns out. So if multiplying creates an exponential, you would expect that dividing would create an inverse exponential, which is what we call a logarithm. And in fact, that's the case. So if f of 0 in this case is 0, okay, f of 1 is also 0. What about f of 2? f of 2 is 1 plus f of 1, so that's going to be 1. f of, never mind 3 for a minute, f of 4 is 1 plus f of 2. 1 plus 1 is 2. f of 8 is 1 plus f of 4, which is 1 plus 2 or 3. We're getting the inverse exponential, the logarithm. And so if we do 8 here, there it is. Now what's happening here is you're getting the integer logarithm. So in fact, when you get values like, if I did f3, that's 0, 1, 2, there's f of 3, it's still 1. But basically it's an inverse logarithm. And then what's making that an inverse logarithm is that we're dividing by 2 each time. So we're rapidly converging. X is rapidly getting down to 1. All right, so what's going on in this case? Well, f9, what's going on? We're going to do f9x minus 1 plus f9x minus 2. We've seen this one already. You should totally know what's going to happen when I put 9 here. You get the Fibonacci numbers. Okay, so for f10 is x times f10 of x minus 1. So we've seen this one before too. What function is x times the same function of x minus 1? And that would be factorial. 1 factorial, 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. All right, so f11 is going to take 2 values. And never minding the first case, we'll ignore the negatives for now. If y is 0, return 0. Otherwise, it returns x plus f11 of x and y minus 1. Well, let's just think through f11 of, say, 2 and 3. That is 2 plus f11 of 2 and 2, which is f11 of 2 and 2 is, come in here with 2 and 2, you kick down here 2 plus f11 of 2 and 1, which that is, when x is 2 and y is 1, you get 2 plus f11 of 2 and, oh, pardon me here, of 2 and 0. And finally, since y is 0, this one is 0. Okay, So that is 0. So now we have 2 plus 0, so that expression is 2. And now we have 2 plus 2, so this expression here is going to be, let's see, that expression there was 2, so this one was 2 plus 2, so that expression is 4. And now we have 2 plus 4 for this one, so that's 6. So the whole thing is 6. So what happened was we were adding 2 over and over again. And sure, now let's go back and think about what's going on. What's really happening here is x never changes, never. And all that's really happening is y keeps counting down by 1 until it gets down to 0. And all you do is keep adding x over and over again. So you're adding x a total of y times. This is going to be the product of x times y. And if we run f11 of 5 and 7, we get 35, the product of x and y. So f of 12, like f of 6, is a little cutesy. And so we wouldn't expect you to figure this out. But it's very similar to f of 6, actually. So what is x minus 1 times y minus 1? Well, that equals x times y minus x minus y plus 1. Solve for x times y, and you get that x plus y minus 1 plus x minus y times y minus 1. So in fact, if this function computed the product x times y, then this function of x minus 1 would compute this product, to which we add exactly x plus y minus 1. So we would expect this to, again, be the product, which in fact it is. Once again, if you didn't follow that, don't worry at all. You can pretty much skip f6 and f12 and not worry. f13 you should be able to figure out. So f13 takes in a list. If the list is less than length 2, so 0 length 1, it just returns an empty list. Otherwise, it recursively calls everything from the element 2 onward, and then appends to the end of that element 1. Element 1 is the second element. So if we had a list like, well, 0, 1, 2, 3, 4, 5, what's going to happen is it's first going to recursively compute off of 2, 3, 4, 5. Okay, let's go ahead and do that. It's going to recursively call 2, 3, 4, 5, which is first going to recursively call f13 of this, of 2 onward, which is 4, 5. And now, because it's still not less than 2, it's going to recursively call f13 of 2 onward, which is just the empty list. All right, now finally we get to the empty list, and that's less than 2, so it returns the empty list. So this returns the empty list. To that empty list, when L was 4, 5, we recursively called f on the empty list, and then we added L of 1, which is 5, which means that this one is going to return, it returns the empty list plus the list 5, which is just the list 5. That's the result of this call. Now we're back out to another level when we called it on 2, 3, 4, 5. It recursed and computed 5, and it's adding on L of 1, which is 3. So this one gives us 5, 3. And now we're out one more level. We're at this level. It recursed here to give the 5, 3, and it added it on the second element, which is 1. And now we see what's going on. We're getting every other element coming backwards in reverse. So when we do f13, indeed, that's exactly what we got. Every other element, because this did range of 20, 0 to 19, and we got every other element coming down in reverse. So that's all the functions here. You might want to review these a little bit on your own time. You want to tweak them a little bit. What would happen if I did f minus 2? What would happen if I did that? What would happen if I did that? And now if I do 1, it doesn't work. And you might say, what just went wrong? It's an interesting question. Actually, in this case, we jumped our base case. and there. So there's these interesting ways that you can play around with these functions to see what happens when you change these values. Sometimes it's interesting, sometimes less so. In any case, that should show you some of the math behind recursion.